They know my story. From old dogs to do. I be hustle to work daily.
Hi guys, my name is Nako Nakatsuka. I'm a 4th year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we'll talk about Gibbs free energy, which is another thermodynamic function, but luckily the last one we're going to talk about in this section. And so the Gibbs free energy is the thermodynamic potential that measures the usefulness or process initiating work that's obtainable from a thermodynamic system. And this has to occur at a constant temperature and pressure. So if you look here, these are some very useful diagrams where we go from reactants to products, and in an endothermic reaction, this is a jump in energy going from reactants to products, whereas for an exothermic reaction, which is releasing heat, we go from reactants at a higher energy level to products at the lower energy level. So let me write down the axis here for you, which is energy, so this makes better sense. As you can see, the Gibbs free energy, or the change in the Gibbs free energy in this case, is the change in the energy level from the reactants to the products. So this part is going to be the activation energy, which we'll talk about in greater detail later on. But basically, the activation energy is the energy that has to be overcome for a reactant to go to a product, so this little hump, whereas the delta G value is the difference in energy between the two energy levels. So let me remind you that this is going to be at constant temperature and pressure, and Gibbs free energy is written as G equals H, which is enthalpy, minus Ts, where T is temperature, S is entropy. So as you can see, now everything's coming together, right? By looking at Gibbs free energy, we're combining our understanding of enthalpy and entropy. Okay, so now from here we can write down the change in Gibbs free energy as delta G equals delta H minus T delta S. Temperature remains constant, but everything else can be written as a change. So we mainly use Gibbs free energy because most reactions and nearly all biochemical reactions occur at constant temperature and pressure. So how does this Gibbs free energy relate to the spontaneity of a reaction? And remember, when we talk about spontaneity, we're not talking about the speed of the reaction. We're talking about whether that reaction is favorable and whether it's actually going to happen. So when we look at this, let's write out delta G equals delta H minus T delta S again. And then let's divide both sides by negative T. So if I divide delta G by negative T, this by negative T, and this by negative T, this will cancel out, right? And from here, we can write this out as delta G over T, but now it's negative because we divided everything by negative T, which equals negative delta H over T. And then we just have plus delta S. So now I want to also write this as the delta G of the system, the delta H of the system, and the delta S of the system as well, so that I can write out this part as something separate. So remember this relationship where delta S of the surroundings can be written as negative delta H of the system over temperature, which is exactly what we have. So now we can actually rewrite this as negative delta G of the system over T equals delta S of the surroundings plus delta S of the system. So doesn't this look familiar? When you add the delta S of the surroundings with the delta S of the system, this is equal to the entropy change of the universe, right? So basically, using this relationship right here, I'm showing you why delta G values can be related to spontaneity. Because for a spontaneous process, delta S of the universe is going to be positive, right? That's something that I talked about before when we were talking about entropy values. And so In order for something to be spontaneous, the entropy of the universe must increase, meaning delta G has to be negative, right? Since there's a negative sign right here, it has to be the opposite of the value of the delta S of the universe. So now, understanding that delta G is always negative for a spontaneous process, we can actually now use different signs of the delta H, delta G, and delta S values to predict the spontaneity of a reaction. So now here's a table summarizing what I was talking about before, where we can predict whether a reaction is going to be spontaneous or not by looking at the enthalpy values and the entropy values. And sometimes it's temperature dependent, depending on the signs of the enthalpy and the entropy. So remember, for a reaction to be spontaneous, delta G has to be negative, right? So let's look at this example right here. Delta H is positive and delta S is negative. In this case, if you have a positive number and you're subtracting a negative number, regardless of what temperature is, you're going to end up with a positive delta G value, right? Thus, delta G is positive at all temperatures, and this is not spontaneous, which I'll show from now on by writing a cross. So let's look at this example, where delta H is negative and delta S is positive. If you have a negative number and you're subtracting a particular value for it, whether it's a large number or a small number, the factor of temperature doesn't even matter. You're going to end up with a negative value. And thus, delta G is negative at all temperatures, and this is spontaneous. So as you can see, we're predicting whether the reaction is going to be spontaneous or not spontaneous based upon the signs of these two values alone. But what if you have, in this case, positive delta H and positive delta S? In this case, it's actually going to depend on what the temperature is, because depending on what factor you're multiplying the delta S value by, you might end up subtracting a very small value or a very large value. So in this case, delta G is positive at low temperatures when you're multiplying by a very small number, and negative at high temperatures. So in this case and this case, you're not going to be able to tell unless you actually solve the equation by putting in the temperature value. But as you can see, for any different value that you're given for the enthalpy and the entropy, you can predict whether a reaction is going to occur or not. So if G, or the Gibbs free energy, is the energy minimum, then any negative change must be spontaneous. And when G is at a minimum, this means that the system can no longer change. And so I can write this out for you as delta G, or the change in the Gibbs free energy of the system, is 0, aka the system is at an equilibrium. So remember, this 0 up here indicates that a substance is at a standard state, right? We talked about this before when we looked at enthalpy as well as entropy. So delta G naught cannot be measured directly, unlike heat flow in a calorimeter can determine delta H naught. So these values can actually be determined, but this cannot be directly measured. So we can actually calculate delta G naught by using standard enthalpy of formation and standard entropy values of reactants and products. So you must remember these equations, right? Where the delta H of the reaction is the sum of delta H of formation of products minus the sum of delta H of formation of the reactants. We went over this when we looked at enthalpy. And you must also remember that the delta S of the reaction can be calculated from using the standard values of entropy, where it's S naught product minus S naught reactants. So by using these two equations, we can actually solve for delta G in its standard state, because delta G of the reaction can be simply written as delta H of the reaction minus temperature delta S of the reaction. So as you can see, whenever you write out any reaction, whether it's G equals H minus TS or involving the change in the energies, as long as each individual component matches up, you can rewrite it in whatever form you want. So in this case, we're writing it out as the Gibbs free energy in its standard state for the whole reaction, and that's why we put it in the same format for the enthalpy and the entropy. So since free energy is a state function, we can also calculate the delta G total by adding or subtracting the delta G of reaction 1 and delta G of reaction 2. So it's additive, just like everything else that we've been looking at. Reaction 1 plus delta G of reaction 2. And this leads us to looking at the standard free energy of formation, written as delta G is the sum of the delta G of formation of the products minus the sum of the delta G of formation of the reactants. So exactly the same as what you saw for enthalpy and entropy you can do for Gibbs free energy. So now using this understanding, let's do a couple of practice problems.